I'd like to start this afternoon's session. I invite Thomas Klose to start.
Thank you very much. I also would like to thank the organizers for the possibility to speak. I have chosen to present a little computation which checks in a direct way the quantum integrability of strings in AdS 5 process 5 in a certain limit, of course, which I will discuss. This is a project together with Valentina Giangreco-Puletti and Olof Olsson-Sachs from Sweden. And actually I have presented this work precisely here already a month ago, but given the different audience, I think it's allowed to summarize this once more. Another a big thank to Tristan McLaughlin, Joe Minahan, Radu Reuban, and Kotsin Zarembo for further collaborations where I learned all these things about this worldsheet scattering and near flat space limit and all this. So from the fact that you all come here to this conference, I can conclude that you're already pretty much convinced that string theory is quantum integrable. But still, we can do a little computation as a check given by this equation here. The right part you recognize as the Young-Baxter equation, which is necessary but not sufficient condition on the two-particle S matrix. If you want to do something sufficient, then you can show that for an n-particle amplitude, the scattering is described by all you know from the two-particle scattering. For the case where the particle number n is equal to 3, this is depicted here on the left-hand side. So n is also the case we look at here today. Now, the statement, like summarizing the whole talk in one sentence, is I show the factorization of the three-particle worldsheet S matrix in the near flat limit of AdS 5 crosses 5 in a one-loop computation in the sigma model. So now you know everything. I mean, this is the statement of the talk, and I will make 3 points. I want to basically recall the connection between integrability and the existence of charges to the factorized scattering. Then counting the elements of the three-particle S matrix, you find a very large number. So the 16 is because you have 16 particles, 8 bosons, 8 fermions, 3 because you have 3 particles, and then it's a mapping from a 3 particles in state to a 3 particle out state, so it's squared. So these are the components, but only 4 of them are independent. So to show the factorization, you in principle, because of the symmetries, you just need to do, you need to compute 4 scattering cases. And then I want to show a little bit, this is more the technical part, but not too technical, hopefully, is how this comes about from the Feynman diagram computation. I mean, how do you see that they're the 3 body processes factorized in 2 body processes? Okay. I want to illustrate the scattering by a little cartoon. So we have Alice and Bob in a flat space and a quantum string, and they send signals back and forth, and these bumps, these excitations, travel dispersionless along the string in this flat background. And when 2 of them meet, then they don't feel anything. This is a free and linear theory, so they just go through each other. If you put them in a curved space, then it's pretty unclear what's going on there. You cannot even see really what is an excitation and what not. And they, I mean, by far not dispersionless propagation and interaction, you don't know. So we don't know about the spectrum. No, I didn't say that before. Quantizing, I mean, you quantize every mode and you know the spectrum immediately. In the general case, you don't know it, but if you choose AdS 5 crosses 5 as a background, something happens. This is this integrability story. So you have these excitations that also propagate dispersionless with different speeds, and when they meet, there is a little bit of interaction, but not too much. They keep their shape. They go through each other with a little phase shift, and that's what we want to compute. This phase shift is the is this scattering matrix, essentially. So that's what this is about. Let me first summarize briefly what we know about the integrability. So classical integrability of the string theory. It follows from the fact that the trace of the monodromy matrix is conserved and generates for us an infinite number of conserved charges. Then we have this algebraic curve describing the classical strings. Somewhere in the transition between classical and quantum, when you quantize these equations, you end up with Bethe equations for the quantum string. And from the fact that these Bethe equations work, you can already conclude something about the integrability. So they have to work for 2 excitations, but they do not have to work for more excitations. Like the 3 particles don't have to be described in general by the 2 particle processes. So when you check that the energies that you compute explicitly from the string for multi-excitations and compare it with what you get from the Bethe equations, and you find agreement, then this is an indication for the integrability. Then we have Berkowitz's proof of the quantum consistency of the AdS string and the existence of the higher charges, but in the pure spinor formulation. Previously we had done something like this, shown that there's no particle production, but it's only in the bosonic sector in semi-classically. So it's basically, today this is an extension of this work. And another comment, so taking this monodromy matrix, it has been shown that this doesn't have any divergences, so it makes quantum mechanism sense. And so we expect to have these charges at the quantum theory too. Okay. Now, integrability and factorized scattering. Because I want to do a different approach here. The statement is the following. So if you have these higher charges, and let's say we have a Lorentz invariant theory, because at that time this is what people are interested. Then number 1 is there's no particle production or annihilation, so the number of particles before the scattering is the same as after. And the momenta of the individual particles is conserved. So the set of in momenta is equal to the set of out momenta. I drew here, for the case of n equals 3, the phase space. So these are the momenta of the out particles. And they are restricted by the charges. So like the sum of them has to be the total momentum. That's the blue plane. The sum of the squares or so the energy got to be a fixed value. That's the red sphere here, or 1/8 of a sphere. And all the higher charges constrain these momenta. And you end up, in this case, with 6 points. These 6 points are the 6 permutations that you can have for 3 momenta P1 to P3. And that's basically all that you have. So you can only permute the momenta. And that's because you have these charges and you have to satisfy certain equations. That's the momenta. You can also say something about the S matrix. So if you now scatter these n particles, so here 4 in, 4 out, then this process really factorizes, if you look into the interaction, 2 by 2 scatterings, and the number you get from counting the number of crossings. So, and you can make it precise. In this Lorentz invariant theory, 2 higher charges are enough to have this factorization. So you know that we don't have a Lorentz invariant theory here, but I'm not going to use this theorem anyway. So I don't want to show that there are charges and then conclude the factorization. I want to compute the factorization directly.
Should that read monogram and scalar and vector? Tensor must be.
What tensor, right? No, I guess it was a second rank tensor. I think it is a second rank tensor, when I recall correctly. So, Okay, this was just a bit background how you connect charges and factorization. Now let's talk about the string theory, and I want to recall the labeling and the symmetries. So you start with the sigma model on this coset describing this AdS5 crystal 5 and the fermions. You have the PSU 2,2/4, which after choosing a certain gauge breaks into PSU 2/2 squared. And I use one color and another color for the two different copies because, I mean, they also carry dots, but you don't see them very well. So we have these two copies of PSU 2/2 as the symmetries, and that so every field has two indices, the blue and the red one. And if both of the indices are bosonic or both are fermionic, you have a bosonic field, and if they are of either kind, then you have a fermionic field. Now, Nicholas showed that this algebra becomes centrally extended, and these people showed that by considering the string theory and the algebra that you have further generators there. So there's an R cubed, which will become important on the next slide. But so far, okay, we have the symmetries, and the S matrix maps the in state, where you have, I mean, a two-particle in state to a two-particle out state. The momenta are P and P prime, and they are conserved. So after the scattering, you have P and P prime again. But the indices can change. So the S matrix tells you how the flavors of the fields hop between the different momentum lines. So from here you can count how many components. But the nice thing is that this big PSU 2/2 squared S matrix group factorizes into two copies of a PSU 2/2 S matrix. I should note this is not the factorization, the multiparty factorization, it's another one. The multiparty factorization factorizes the three-particle S matrix into two-particle S matrices. Here I just split it according to the symmetries. So now we can look at one of these factors, and I want to count how much freedom we have. So I guess you have heard before that the S matrix, the two-particle S matrix, is fixed up to this scalar factor, right, that we are all after. Let's review this argument. So I look at one of these matrix factors, and I multiply two fundamental representations because I have two particles. And I multiply these young tableaus, and I get these two irreducible representations of SU 2/2. But then, if you have the central extension, the supercharges of the centrally extended algebra are more general than the ones that for the non-centrally extended one. So they can link these two things into one irreducible representation of this central extended algebra. Okay, so if there's only one irreducible representation of this in this tensor product, and this S matrix is supposed to be an invariant operator, then it must be proportional to the projector onto this representation. So that's how you count this. So there's one normalization function left. And let's repeat this for the three-particle case. So I multiply now three fundamental representations, and I find for the central extended algebra two irreducible representations. So I know, okay, it can have two projectors, and since this was only for one S matrix factor, I will have four for the full S matrix. So these are the four that I referred to in the beginning. Okay, so like we can compute these four functions by considering certain processes. I call them highest weight processes. They have, so these are eigenstates of the S matrix, and split out these coefficients that we want to compute. So we computed these C's by just sandwiching between these states and pulling out delta functions. And also you compute it for mixed processes just to see if all the symmetries work, and also you want to see how it works for the external fermions and interactions between them and how you change fermions and bosons and so on. But all this works. So having computed these amplitudes, you see, okay, they factorize nicely. So that's the result, right? We do this in the near flat space limit. So this is the action given by Maldacena and Swanson. And the fields that we had before, the y, z, psi, and upsilon, they are now written in terms of x's and psi's. And okay, let's see where we are. So this is the dispersion relation for AdS50. And down here, for small momenta, we have the plane wave theory, free massive theory. And up here are the giant magnons with the high order interactions. And this near flat space limit sits in between, where it's more than trivial, but less than too complicated. So you have quartic interactions. You see we have here only quartic interactions. And this where you can nice computations. And a few statements. The decompactification limit that I need for S matrix computations is already built in this limit. So my world sheet is infinitely long. I will integrate this action from minus infinity to infinity. So I can have asymptotic states that come. The interactions are not Lorentz invariant. You see d minus squared. There's no balancing between d minus and d plus like in the free part. So the free part is okay. These interactions break Lorentz invariance. The coupling constant gamma, third point, is actually just a fake coupling constant. The interaction strength is measured by the value of the momenta. So it's like a low momentum expansion, but for power accounting, it's nice to have it. So you scale it in, and then you do an expansion in this gamma. And you think of gamma as being proportional 1 over root Toft coupling. It decouples left and right movers, so the right movers are free. There is no right mover in the interactions. This theory is UV finite. It's pretty nice if you do computations, and it's a reduction of the classical theory, but it seems to make sense quantum mechanically. So it's a quantum mechanically consistent reduction, which you check by explicit computations, at least up to 2 loops.
Just a minor question. What are the time space isometry?
Same.
The whole PSU224.
Yeah. So, yeah, I'm not sure how to take the limit of the geometry and then put the string theory on top. It's first doing the string theory in the AdS factors of 5 with the full, then doing the gauge fixing, and so you break a little bit of it, and then taking the limit, right?
Well, it's not manifest, but it's all there.
Yeah, supposedly, yes. So we do the computation in this limit, and how do you actually do it? So that here these two-body S matrix coefficients you find in the 4-point amplitudes. So now sandwich between the two particle states, the S matrix, and do Feynman diagrams. If you have only 4 particles, then the energy momentum conservation, this delta function, gives you already the conservation of the individual momenta that I said before. Integrable theories, you have conservation of individual momenta. For the 2-to-2 scattering, this is kind of trivial, and your amplitude has always this form, and the two-body S matrix you can identify, you can compare immediately. In the 3-particle case, this energy momentum delta function is not sufficient, right? You have 3 in, 3 out, and this does not factorize. So the fact that the amplitude anyway is of this form where you conserve individual momenta is the first non-triviality. But it just comes out. If you compute this, there will be another delta function popping up, and then it has this form. But this is a non-trivial check. And then if you have this, then you compare these two together, and the second non-triviality is that this 3-body S matrix is really the product of the two. So this is the equation corresponding to the picture of the red dots in my first slide, right? So or graphically again, it's that these are fixed momenta, P1, P2, P3, and these are flavors hopping between the lines, and they hop here the same way as they do after considering these 2-body interactions. So and this matches the second non-triviality, and we check this and it works. I want to show you in the last part how these extra delta functions come up, because it's sort of interesting. So at tree level, you have this kind of diagram, and at one loop you have 2 different kinds, with a little loop here and a vertex, or a big circle. And now if you compute the amplitude, wait, that's this. Let's say energy momentum conservation restricts your particles to lay on this curve. So D, E, F are the out momenta, and this is momentum conservation, energy conservation, and so you have the freedom to be somewhere on this curve. This curve I unwrap here. So this is the value del D, E, F subject to energy momentum conservation. And then you compute the amplitude, whatever, tree level, one loop, you find typically something finite and then divergence is somewhere. If you sum all the terms, the partial amplitudes, then this finite stuff cancels. It cancels to 0, and you're left with these divergences. So at 6 points, you have a divergent amplitude. And now you're supposed to subtract, to factor this divergence compute the residue. And then what you have in front, this is the three-body S matrix. And this magic formula is this. If your propagator, which is this propagator here, when it goes on shell, it produces the divergence. And you can subtract, you can separate the finite piece and the divergence using this formula. Very simple, but this works. In this case, it does the trick for us. The finite terms, as I said, sum to 0, and the extra delta function that you need is here to do the factorization in the individual momentum. Time for a side remark. If you have Sine-Gordon and you do the three-particle scattering, it looks the same, but then this doesn't sum to 0. Here you have some constant term plus the divergences. If you then include a 6-point vertex, which will be a constant for the three-particle scattering, you can put this down to 0. Oh, that wasn't so good. I was considering phi 4. I said I was considering Sine-Gordon. I was considering phi to the 4. This near flat space is very similar to phi to the 4. And there you find the constant. If you put in a 6-point vertex, then you can make it to 0. If you keep on going, then you generate higher terms, and then you end up with Sine-Gordon. I didn't mean to start with it, right? So in Sine-Gordon, everything factorized is good. Okay. Right. You see here, here you see it's this propagator that does the divergence. Here's this propagator. This bubble is finite, and here that's a bit funny, and you get it from a cutting rule. So it's like an old cutting rule that tells you that every one-loop diagram in a 2D theory can be translated into 2 tree and a single bubble diagram. And I guess I don't go through it, but if you apply this cutting rule to the circle here, you find tree-level diagrams plus a finite bubble, and these propagators here correspond to one of the 3. So you translate it first into something that looks like a tree diagram, and then this is the one that does the divergence. Right. A final observation. So we compare the Feynman diagram computation, the amplitude, to the product of the 2-body S matrices. So the 3-body S matrix is 3 copies of the 2-body S matrix. If we expand this in order of gamma, so no order of gamma, 2 orders of gamma, sorry, 1 order of gamma, we choose one to be a vertex and the other one to be trivial, then you have a picture like this. At second order, you can either choose a gamma squared here or 2 gammas for these two, and it looks like this. And at cubic order, you have 3 different choices. They correspond to, so this, and this is disconnected here. Probes just the 2-body S matrix, right? The 3-level, 1-loop, 2-loop level of the 2-body S matrix that we checked before. And the others are connected diagrams, and they check, 5 minutes. They check the factorization. This corresponds to the tree level, and these two to the 1-loop level. And now it is suggestive to identify this term in the expansion of the three-body S matrix with this kind of diagram, because it looks like this. There's a single vertex here and there, and a bubble, which is the order gamma. And this looks like this, with the circle and the circle here. So we thought, okay, can we, instead of comparing the whole series to this, identify these two and these two individually, which doesn't have to be the case. I mean, it's just a term, I mean, a few terms in the Feynman diagram expansion, so they don't have to match, but it looks suggestive. And it does work for the very symmetric processes, like all bosons. And for all these highest weight processes, it does work. And so we thought, oh, this works in general. Oh, we found something. No, it is just not true. If you have a mixed process, then you cannot identify individual diagrams with this. So that makes it a bit more non-trivial and more interesting. And it's kind of clear. This is all off-shell, and this is really an on-shell propagator. So there is a difference. And it wouldn't, such an identification wouldn't even work at higher orders. I summarize. This is saying that you cannot identify separately. We have shown the factorization of the three-particle S matrix in this near flat space limit to the one loop order, and seen that this turns effectively into this object. Computed for the highest weight amplitudes to fix all the freedom in the three-body S matrix. Computed for some mixed processes to check the supersymmetries. And this is really a very direct check of the quantum integrability, albeit just in this near flat space limit. And then as a future thing, you could extend this to higher loops, to more particles, to the full theory, whatever you want. This is probably all very hard. And like we believe that this works for higher loops, more particles, and the full theory. But what about the finite size corrections? That would be very interesting. Like, there's no real asymptotic state for this. So can we make sense of the scattering at finite size? I want to finish with this question.
I think there's time for one question.
What happened with the level matching condition in this model?
In the near flat space model, if I have a decompactified worksheet, right? So I don't need to have a level matching condition because I don't have it closed.
How do you know it's decompactification?
Basically, because I don't want to have a level matching condition, I make it decompactified. It wouldn't make sense if I impose level matching condition. My theory would be empty because everything is going one direction, right? I have this near flat space limit suppresses, like say, right movers and enhances the left movers, and everything's going one direction. And I couldn't impose level matching without, I mean, making the theory empty. So the trick is to have it in infinite worksheet that you don't have to impose level matching. And in that sense, it's built in. But we don't mind because we do scattering and we want to have it infinite anyway for the asymptotic states. This question, okay, I don't know how to answer this. Yeah, I guess so, because there shouldn't, asymptotic states means you can go to a time where there's no interaction before that time. Like everything is separated, I mean, right? So asymptotic minus t. But on the circle, you cannot separate. I mean, they go around, around, around. There's no asymptotic regime like that. Like I have separated them, but then they meet again on the other side, or.
Okay, thank you very much.